I'm sorry. That threw me off. You just asked me if I feel pretty right now. Particle. Whenever I'm doing calculus, a particle travels at a straight line. Okay, so this looks like it might be a PVA problem. You guys familiar with PVA problems?
Yeah.
That's position, velocity, acceleration. If you want to move from one function to the other, it's just derivatives and antiderivatives. The derivative of position is velocity, derivative of velocity is acceleration, or you can go the opposite way. You just got to remember, if you ever do the antiderivative or the indefinite integral of, like, let's say velocity with respect to time, you're going to get a of t plus c. You're always going to have that c. Don't forget about him. Okay? All right. So we have a constant acceleration of 3 meters. So we know what the a is. A of t is a constant. It's 3. And it tells you the units, just noting, because the unit sometimes helps in really confusing problem situations. Because if a problem is really confusing, pay attention to units. Because the units will tell you if you have a velocity or if you have an acceleration, whatever. This one is per second, or per second squared, which means it's acceleration. If the velocity of the particle is 10 meters per second at 2 seconds, okay, so velocity, let's see, velocity at 2 seconds, oops, I'm going to write 2 instead of t, at 2 seconds equals 10. So that's a point on velocity. I like writing it like this, though, because we have points that are on acceleration graphs or position graphs or velocity graphs. This one kind of makes it clear, like, hey, this is a velocity point right here. Okay, how far does the particle travel? Now, because it asks how far, which function are we thinking about we're going to need? Are we going to need position, velocity, or acceleration? We're going to need position. Position tells you how far. But we do have more tricks up our sleeves if we can't get a position function. But let's go on. During the time interval when its velocity decreases from 4 meters per second to 10 meters per second. So those are velocities, right? We already know what the t is at 10 meters per second. We do not know what the time is at 4 meters per second. So this just got really weird, okay? Now, if I'm a normal student, the first thing I'm going to try to do is I'm going to try to find a velocity function, and then I'm going to try to find the position function. So let's try that and see if that works. I can already see that it's not because it gave me weird information. So here we go. This is our acceleration. That's what we're starting with. So that means velocity would be 3t plus c. Okay, you guys know how we got that? We kind of like talked about that earlier. Okay, when you do the antiderivative of, oh wait, totally did that wrong. What's the antiderivative of velocity? It's not acceleration. Wow. It's position. Okay, woo. All right, but this one is the antiderivative of acceleration with respect to t. That would give you velocity plus c, okay, which is what we got right here. Okay, so we don't have a constant, so we don't have a complete velocity. So taking the antiderivative of this again won't really help us yet because we know we're going to have multiple c's. So how are we going to find that c? That's right. We're going to use this point right here. Okay, so I know that velocity would be 10 if we plugged in 2. That's what that says. And so c is going to equal 4. Is everybody cool?
Yep.
So velocity will equal 3t plus 4. Got to make sure t has that foot on there, otherwise he looks like a plus sign. Okay, so now let's try that again. Let's do this guy right here. If we do the antiderivative of velocity, what will we get? We will get a p of t equals 3 divided by 2, t to the second power, plus 4t plus c. Because I'm not writing it all. I'm not being very excessive in writing all of it to show you guys we are doing an indefinite integral. But look, I got a c. Okay, so how would I find that c? Do I know a position? I don't know a position point. Like, you know how the velocity one we knew. We don't have a position point, so we can't find the c right off the bat. So instead of doing an indefinite integral,
Oh, you're going to do a definite integral.
we're going to do a definite integral. Okay? You're like, I knew that. Oh, dang it, man. Okay, so if I was doing the antiderivative of velocity, Okay, there's your velocity, right? Everybody's cool. What are the two t's that we are doing? Because it says right here, the time interval when its velocity decreases, it's a time interval, when the velocity decreases from 4 meters per second to 10 meters per second. Well, I know the time for 10. Do I know the time for 4? Oh, but can I find it?
Yeah.
Yes, I can. I can go back to this guy, and I could plug 4 into that, right? The velocity is 4, to find my t. All right, so I would subtract 4. I would get 0. So what is t?
0.
Oh, cool. So we're going from 0 to 2. Is everybody cool?
Yeah.
I got that from this 2 right here that we knew already, and then we found that over there. Okay? So we're going from 0 to 2. So I just have to do the antiderivative of this and then plug in those things. So the antiderivative is the same as what we just did. So it's 3 over 2 t squared plus 4t, and then we're going to plug in 2 and 0, right? Because no constant, because we have a definite integral. When I plug in 2, that would be 3 over 2 times 4 plus 4 times 4. Nope. Plus 4 times 2. And you guys are not paying attention. You guys totally didn't catch that.
Okay, well,
Actually. Okay, so 0, if I plug in 0, I get 0. So it looks like we're done. I just have to simplify this. So this 2 cancels out with that 4 to become a 2. So we have 2 times 3, which is 6. 6 plus 8, which is...
14.
Notice that the units is meters. Okay, so PVA, this would be meters. This one is meters per second, and acceleration would be meters per second per second. Oops, that's not an S. Or the cooler way, meters per second squared.